everyone. Welcome to another session of Circuits and Networks. In today's three-phase circuits class 4, we are going to see a simple problem which is related to star and delta network. Here, the power is to be calculated, and later on, one of the impedance, or what we can say, one of the leg parameters resistance, if at all it is removed from star network or from delta network, then how the power will be. It will be increased or decreased. That is what we are going to see in today's class. The question is given as three 50 ohm non-inductive resistors are connected in star and delta form across 4 and 15 volts 50 hertz three-phase supply. We need to determine the power drawn from the supply in each case. That is the first requirement. If one of the resistance gets open circuited both in star and delta, then what would be the value of total power drawn from the mains in each of the two cases? So as the problem you can see, it is star connected network and it is delta connected network. So we need to calculate the power in star as well as in delta network. That is our first requirement. So let us do that first. So for a star connected load, the input line voltage is 415 volts, frequency is 50 hertz, and impedance overall we are taking in Z phase form, that is 50 ohms. And in star connected network, V phase is equal to VL by root 3. So V phase would be equivalent to 240 volts. So once the V phase is obtained, we can easily calculate the I phase related to star load, which is nothing but 240 by 50 ohms, which is nothing but 4.8 amperes. Now we are done with V phase and I phase, and we have cos phi is equal to 1. Why the cos phi is equal to 1? Because it is a resistive network. All the impedances actually are having 50 ohms as resistance. So that is why there is no phase lag or phase lead between voltage and current. That is why the value of cos phi is equal to 1. In that case, the power would be equivalent to root 3 VL IL cos phi. So the value of VL is 415 volts, and the value of I phase or line current are one and the same. That's why we are taking the value as 4.8. The cos phi value is 1. So overall power for star load, it is obtained to be 3.45 kilowatts. Let me treat this equation as 1 and remember this equation as well as the value of power. Later on we have to see what is going to happen about the power when one of the resistance is removed from the star load. Okay. Also for delta load, we should remember that line voltage and phase voltage are same, and that is why the value is 415 volts per phase voltage. What about the phase current? The phase voltage by the impedance of the circuit, that is Z phase. In fact, that is nothing but resistance value. Here it is given in to be equal. So 415 by 50 is nothing but 8.3 amperes. So we require to calculate the line current because in delta network, line current and phase current are not the same. So line current would be equivalent to 8.3 times root 3 is nothing but the relationship between phase and line current. So the line current would be equivalent to 14.37 amperes. Since the entire load is resistive in nature, that's why the cos phi value is 1. And again, by substituting the value of power, we'll get root 3 VL cos phi, whose nothing but value is nothing but root 3, VL value is 415, IL value is 14.37, and the cos phi value is 1. The power is here obtained to be 10.329 kilowatts. So let me treat this equation as 2. Now remember, when the star load is given, the power is 3.45 kilowatts, and when the delta load is taken, the power is 10.329 kilowatts. Now what happens if one of the resistors is removed from star and delta network? So let us take for the star network. So I have removed the line B, which is connected here, that has to be removed. So one of the resistance is removed in star network. So the rest of the value is nothing but the phase voltage is applied across AC. Now 50 ohms and 50 ohms are connected in series. So entirely 415 volts is applied to these 100 ohms which are in series. So I phase will be equivalent to B phase by Z phase, which is equivalent to 415 by 100. 50 plus 50 becomes 100. So current value here we got as 4.15 amperes. In fact, power is nothing but equal to BL or B phase I phase. Now we are not talking about the phase values. We are having one positive and one negative. We are treating the network like that, and we are calculating the power because the third line is removed. So the power will be equivalent to 415 multiplied with IL, which is nothing but 4.15. So this value is nothing but 1.72 kilowatts. Now but remember, in the star connected load the power was approximately 3.45. So half of the power is reduced when one of the resistance is removed from the star connected load. Now take the delta network and remove one of the resistance. So here we have removed the resistance which is placed over here. Now we can see 50 ohms at a time it is shared by 415 volts. So the current would be equivalent to 415 divided by 50, which is equivalent to 8.3. I think you can calculate the value of current between A and C or A and B, that will be the same. Now that is done, and the power will be equal to VLIL or V phase I phase, which is nothing but 415 multiplied with 8.3. So the value is nothing but 3.45 kilowatts. Now in the delta connected network, we got the value of power which is 10 point something. Now here it is 3.4. So overall, one third of the power is removed under power calculation. So this is what happens when you remove one of the resistance from a star network or a delta network. So it's a simple problem. I'm having not enough of time to discuss about further problems. Immediately in the next class, we'll discuss some more problems in three-phase circuits. Till then, please connect to our channel and press the bell icon for the future notifications.